explore cubic functions and optimization step by step. First, if the leading coefficient of a cubic polynomial is positive, the graph always begins in the lower left and ends in the upper right. There are three possible shapes. In the first case, the graph has both a local maximum and a local minimum. It rises from the lower left, reaches a peak at the local maximum, then falls down to a valley at the local minimum, and finally rises again toward the upper right. In the second case, there is a single flat inflection point, meaning the derivative has a double root. The graph flattens briefly and then continues to rise. In the third case, there are no local extrema. The graph bends only once, passing smoothly from lower left to upper right in a simple S-shaped curve. Now let's look at a specific example. Consider the function y equals 1/3 x cubed minus 3x squared plus 2. If this function has a local maximum and a local minimum, what will its shape look like? If there is a local minimum and a local maximum, then the graph will be of the first type. To answer this, we differentiate. The derivative of y is x squared minus 6x, which factors as x times the quantity x minus 6. This means the critical points are at x equals 0 and x equals 6. Next, we apply the second derivative test. The second derivative is 2x minus 6. At x equals 0, the second derivative equals negative 6, which is less than 0, so the graph has a local maximum there. At x equals 6, the second derivative equals 6, which is greater than 0, so the graph has a local minimum there. Alternatively, we can use the first derivative test. If the derivative changes from positive to negative at a critical point, then that point is a local maximum. If the derivative changes from negative to positive, then that point is a local minimum. In this case, the derivative changes from positive to negative at x equals 0, giving a local maximum, and from negative to positive at x equals 6, giving a local minimum. We can also evaluate the function at these points. At x equals 0, y equals 2, so the point 0, 2 is a local maximum. At x equals 6, y equals negative 34, so the point 6, negative 34 is a local minimum. Therefore, the graph of this cubic matches the first case we described. It rises to a local maximum, falls to a local minimum, and then rises again. Next, let's describe the intervals of increase and decrease. Since the derivative is x times the quantity x minus 6, for values of x less than 0, the derivative is positive, and the function is increasing. For values of x between 0 and 6, the derivative is negative, and the function is decreasing. For values of x greater than 6, the derivative is positive again, and the function is increasing. So the function increases from negative infinity up to 0, decreases between 0 and 6, and increases again beyond 6. Finally, we can ask, if the decreasing interval is written as a less than x less than b, with b greater than a, what is the maximum possible value of b minus a? In this case, the decreasing interval is from 0 to 6. So a equals 0 and b equals 6. The difference b minus a is 6. In summary, we have seen that a cubic with positive leading coefficient can take on 3 general shapes, and our specific example shows the case with both a local maximum and a local minimum. By using derivatives, with either the second derivative test or the first derivative test, we can identify turning points, confirm whether they are maxima or minima, and describe the intervals of increase and decrease. And as a final note, If the leading coefficient of the cubic is negative, the whole picture is simply flipped. The graph now begins in the upper left and ends in the lower right, but the exact same reasoning and derivative tests apply. If you fully understand the next lesson on cubic functions, especially the ratio relationships among the local maximum, local minimum, and the point of inflection, then sketching cubic function graphs on an exam will become much easier.